Hi guys, I welcome you all to the second video of Module 6. And here I'm going to introduce you all to this concept of logistic regression. And to start with, I'm going to help you understand that how a binary classification dataset looks like and what is the equation of prediction for a logistic regression, just like how we had seen for a linear regression in our previous module. Then what is this sigmoid function and the log loss cost function? This is something that we're going to cover in this video. So let's get started. So what is this logistic regression? Well, it's just a big brother of linear regression. Or in different words, if I have to explain, it's just an extended version of a linear regression that's actually useful in order to solve a binary classification task. So what am I saying all this? Let's try to understand point by point. So let's say if you're having this type of input data and the output has either zeros or ones to predict. It means there are two classes in this data set, either zeros or ones. Because there are only two type of classes which your model needs to predict, we call this as a binary classification problem. Classification because we are having two classes to predict, binary because we are having two different classes to predict. So that's what we understand by the binary classification problem statement. But now how does this logistic regression work with respect to this? So as I've mentioned that it is an extended version or the big brother of linear regression, the first step that we are going to implement over here is actually linear regression. So I'm going to implement linear regression on top of this inputs that we are getting from this tabular data. And what is it going to give us? If you remember from your previous module, it's simply going to be a multiplication of all these inputs with respect to or associated weights that we give to them and add a bias with respect to that, and that output will be a continuous output. For each and every rows you will be getting some kind of continuous outputs. So linear regression basically gives us continuous outputs. We know this. It's nowhere close to 0 or 1. It can be literally any value between negative infinity to a positive infinity. So the second step that we perform on top of this is the logistic function. We apply logistic function on the output that we get from the linear regression that we apply on this data set. So I'm just going to write this as the apply logistic function. Logistic function. Now what is the purpose of this? The purpose of this is to convert or squash the outputs in between 0 to 1. Which basically means that if whatever was the input that you had from the linear regression, it could be 1 million, negative 1000, literally any value. All of these values will now get squashed between 0 to 1 if we apply logistic function to this linear regression. And that's how we are getting this name that we call as logistic regression. Now, what is the other popular name that we give for this logistic function? We also know this as sigmoid, right? Sigmoid function. Now, how does this look like? This simply looks like this. You are having this y-axis, you are having your x-axis. On this x-axis, you are going to have the outputs you get from the linear regression. As I told, it could be literally any values between negative infinity to a positive infinity. There is a 0 in between. It could be literally any value. But the outputs that you will be getting will be strictly restricted between 0 to 1. So let's say that this is your equation y is equal to 1 and this is your y is equal to 0, as you can see over here, alright? Now how does this kind of sigmoid or the logistic function looks like given all these inputs are given to it? So it's going to look something like this. It's going to start from a very value that is closer to 0 and slowly rise up to this 0.5 value, and then again it's not exactly straight line, it's a curvature if you can see over here, all right, and then again gets flat on top when it's approaching towards 1. So this is how it's going to look like. The graph is not exactly perfect, but let me go to this dashboard and show it to you that how exactly it's going to look like. First of all, what is the formula for this? It's going to be 1 divided by 1 plus e to the power of negative of the inputs, where these inputs are actually the outputs that we get from the linear regression. And this is how the outputs are going to look like for the logistic function or the sigmoid function. And if I just have this y is equal to 1 and also y is equal to 0, just look into the beauty of this. I'll also just go to the settings and convert this to this kind of dotted lines so that it makes much more beauty on top of what we are having already. Let me just zoom in a bit. So what's really happening over here? On this x-axis, we are having the outputs that we got from the linear regression. Now, if those outputs are very positive, you can see that the output of this logistic function is going closer and closer towards 1. And then if these values of the linear regression were, let's say, very negative values, you can see that the values of the logistic function is falling towards 0. And then what really happens if the outputs of the linear regression are closer towards somewhere near 0? Then the outputs are actually closer towards 0.5. So what is everything indicating over here? For that, let me get back to this paint screen so that everything makes sense. First of all, we know that the output of the linear regression will be the input for this logistic function, and the output of the logistic function will be in between 0 to 1. So if I have to write this equation for the logistic function over here, and this is actually your sigmoid, that is sigma. So your sigma, in which if you pass in the values of the linear regression outputs, it's going to be equal to 1 divided by 1 plus e to the power of negative z. Where what is the z? This z is coming from this linear regression, which is actually this matrix multiplication of the input vector with the weight vector, or I should call it as input matrix multiplied with the weight matrix plus the bias term. That output will be fed over here, and all of these values for all the rows will be getting in between 0 to 1, as you can see on the graph over here. So what is this? This is actually referring to the probability of y is equal to 1. This is what you're going to get by feeding in all the different values of the z for every rows. You'll be getting respective outputs, and these outputs are simply indicating that what will be the probability of class y is equal to 1. So if the probability is equal to, let's say, 0. I'll just change the color. If the probability is 0.8, or in other words, if the output of the sigmoid is coming out to be 0.8, it means that the probability of y is equal to 1 for that respective row that you're talking about is coming out to be 80%. So automatically the probability of y will become 0.2. Why? The reason behind this is because it's following a probability distribution, which in itself means that the summation of all the probabilities for all the classes will always add up to 1. So you can see that 0.8 plus 0.2 is equal to 1. And that's how I got an idea that if 80% is the probability of class 1, it's 20% probable that it belongs to class 0. So I hope this is going to make some sense to you, that the outputs that we get from this sigmoid is actually the class 1's probability. And then to get the class 0 probability, you just do 1 minus that output of sigmoid. That's it. So I'll just write that also, that if you want to get probability of y is equal to 0, it's going to be 1 minus sigmoid of z. So this was with respect to probabilities. Now how we can convert these probabilities into classes? This is the final step, because that's what we want, right? We don't want probabilities. We want either class 0 or class 1 to be the output. Now, depending on your problem statement, you can set a threshold value wherever you want. For example, we are having at 0.5. What does this indicate? It indicates that if the value of this sigmoid is greater than 0.5, it's going to belong to class 1. And if the prediction was less than 0.5, it's going to belong to class 0. Remember that the predictions that we are going to get in the logistic regression will always be in the format of these probabilities. Then we basically go ahead and set a threshold value, which is going to convert it into classes. This is something that we get from the logistic regression. So yes, that's pretty much about what all goes inside this prediction pipeline when it comes to logistic regression. The first thing we perform is that with the help of this tabular data, we implement linear regression with respect to that and get this continuous outputs, which are this predictions for each and every rows. Then we take these values and apply logistic function on top of that. And that's going to squeeze all of this kind of predictions of the linear regression in between 0 to 1. And now these are nothing but the probabilities of class 1. After this, you can simply go ahead and set this threshold value. Let me just write it over here. That set threshold. And based on the threshold, if it's greater than that, it's going to be class 1. If it's less than that, it's going to be class 0. This is how it's going to work. Now comes the next part, that is understanding the cost function. We know that we have looked into the mean squared error when we talked about linear regression. You can surely go ahead and try to implement it over here. There is no problem with respect to that. But now, according to researches, we have seen that there is a different type of cost function that works well with this type of logistic regression. Especially when you are talking about with respect to this binary classification and sigmoid activation. And that we call it as a binary log loss. Or let's say, for example, if you are talking about a multi-class classification, for that you simply use log loss. That's going to be basically the categorical cross entropy. Binary log loss is also called as binary cross entropy. Right? So I'll just call it for now. This is binary cross entropy or binary log loss. Now, what is the formula for this? The formula is simply your cost function is equal to, now it's a piecewise function, that if the original value of the class is 0, what is the cost? If the original value of the class is 1, what is the cost? So it's simply going to be that if it's y is equal to 0, it means that I want the logarithm of the class 0's prediction. That is 1 minus the output of sigmoid. Or I can just call it as y cap for now, because y cap is nothing but the output of sigmoid, right? This sigmoid's output is your y cap, the prediction. So I want to find out that what is the logarithm of the class 0's probability. And this is your binary log loss. Now just note that because all of these values are probabilities, these values will be in between 0 to 1. And the logarithmic values in between the 0 to 1, if we pass as an input, will always be a negative value. So to convert it into a positive value, you can have a negative sign over here. Now this defines that if the value of y is equal to 0, then this is your log loss. And if it's y is equal to 1, this will be log of the probability of class 1, which is simply the log of y cap. And again, because this is a probability value, you will just convert it into a positive value of the output by just having a negative over here. Because log of anything in between 0 to 1, it will give you a negative value. And then this negative outside will convert it into a positive thing. So if you want to go ahead and take a look into the Desmos, let me just show that to you. So this was the sigmoid. I'll just get rid of this. And now I'll just call this sigmoid as, let's say, for example, let me just call it as yp is equal to 1 divided by 1 plus e to the power of negative x, right? And this yp I'm going to fit into the minus log of 1 minus yp. What is this? Oops. So what is this red curve that you are seeing? This is the cost function. That's how it's going to look like if we are talking about class 0's probability, that is 1 minus this. If I talk about 1 minus log of only yp, now what is this? This is how the loss function is going to look like if the output class, the true output class, is equal to 1. Now if you want to club this formula into one formula, then that's going to look something like this. It's going to be j is equal to y, or I should say minus y log of y cap minus 1 minus y log of 1 minus y cap. So what does it mean? It means that when the value of y will be equal to 0, it means that this will go to 0 and 0 times anything will be 0. So this factor is out. And then if y value is equal to 0, then 1 minus 0 will what? It will be 0. 1 minus 0 will be 1. So this value is 1, this value is 0. So far what we are having is 0 minus 1 and then log of 1 minus 1. Log of 1 minus y cap, not 1 minus y cap. So 0 minus 1 times log of 1 minus y cap will simply be equal to this. Just like that, if I go ahead and implement y is equal to 1 in this equation, then if y is equal to 1, so this 1 minus 1 will be 0. So this whole term goes to 0. Over here it will be minus 1 log of y cap, and that's exactly what you are having over here, minus log of y cap. So yes, this is how you can basically use your cost function over here like this. This is called as binary log loss, and most of the times you will see that it's performing so well with respect to this binary classification. And yes, as you will go ahead and you will realize that what kind of cost function you can go with what type of functions that you are using on top of this kind of continuous outputs. And after you get this cost, what's going to happen? If the cost is high, you're going to try to minimize this cost. And how do we minimize the cost? By using optimizer. And now what type of optimizer? One of the optimizers that we have covered in the linear regression was the gradient descent. Now, as we'll go ahead in this module, you will see that we are not going to code the whole model from scratch. Rather, we are going to use sklearn library. And inside the sklearn library, I'm going to show you what type of optimizer we are going to use and everything. But now there is one more thing that I really want to show over here is that logistic regression now is not just limited with respect to binary classification. However, in the earlier days, it was created to solve this kind of a binary classification task, but it can also work for the multi-class classification where your labels are now not just 0 and 1. It could be 0, 1, 2, 3 and bunch of zeros, ones, twos and threes are there in your data. Then this becomes your multi-class classification. So even for this, you can go ahead and use logistic regression that is provided by the sklearn library. Now for that, you will need to go to the documentation of it and read a lot of things. But I'll tell you how exactly you can do everything as we go ahead in this particular module. So stay tuned with respect to that. So that's the end of our video over here. And I hope that you were able to understand what is this logistic regression, what is this sigmoid function and a log loss function that is very specific to this type of binary classification problem, especially when we talk about logistic regression.